Interested in writing tests for Flutter and Dart applications, huh? We all know how writing tests is important and how it helps in ensuring software quality, but still oftentimes we might be inclined to skip them unless it's enforced by a company policy or by a grumpy PR reviewer. Why this happens? I feel there is a correlation between the time and mental effort it takes to write tests and the frequency we actually write them. So to facilitate this process, I created this cheat sheet that contains all possible assertions that can be written in Dart and Flutter tests, which you can download and always have at hand when unit testing your applications. Now we are going to dive deep into each of these cheat sheet items, and I'll explain why and how to use them. But before, let me briefly introduce myself. I'm Anna, a cross-platform mobile development expert, passionate about quality software from Ukraine. I currently focus on the Flutter framework, being a Google developer expert in Dart and Flutter. I talk about it at tech conferences, write blogs, create educational content, contribute to open source, and take part in mentorship programs. Follow me on social media to get notifications about my recent work. Now, to make this talk a bit more entertaining, I have a challenge for you. I want you to count how many dashes are there in this video. First few people to tweet the correct answer will receive free tickets to the Flutter Global Summit Senior Track tomorrow. So, this is dash, this is another dash, and this is dash as well. So whenever you see an object or an image depicting dash, add 1 for each such object. Don't forget to tweet the answer and get a chance to win the tickets for tomorrow. Now to the cheat sheet. Let's take a look at our first test. Clearly, this here is an oversimplified version of tests we would create in real life. The result variable here would be a result of some calculations done by the software under test. So when looking at tests I prepared today, always imagine 1 or more lines of code involving some functions invocation instead of just a variable declaration here. So imagine we received a result of some calculations and have to make sure it equals 0. For that, we are going to use the expect function. It accepts the actual value as the first parameter, followed by the expected value. In this first test, both actual and expected values are equal, and thus the test passes. In the test below, the actual value differs from the expected value, and the expect function throws the test failure exception, which leads to test failure. You can see in the test run output, expected 0, but actual was 1. Let's explore the function signature. I put so much attention to it because it is the main assertion function Flutter developers use daily when writing tests. Here are the first 2 positional arguments we have already used. Apart from that, expect function also accepts a string reason and a dynamic skip. Let's see how they are used. In this test, we have the same actual and expected values as before, and I also provide a reason parameter. As you see, it is now printed in the end of a failing test output. As for the skip parameter, I guess it's clear that it allows skipping a single expect function call inside the test. It can either be true or a string with a reason to skip. As you see here, this test would normally fail because expected and actual values are still different, but because the skip parameter was provided and these expect functions didn't throw, the overall test is green. Let's check the expect function signature again. As you see, the second parameter is dynamic, and it's not called the expected value, but it's called mature. It is the most interesting parameter of this function, because in fact, we can put stuff other than just a value in it. And next, we are going to explore a variety of available matchers, learn how to combine them, and how to create your own custom matchers. Yeah, believe it or not, I'm dedicating the entire talk to a single parameter over a single function. Exciting? The first matcher in our list is equals. Let's revisit the first test we created. Expect result is 0. Here we pass integer value 0 as a matcher parameter. In such a case, when the expected value is passed, an equals matcher is used implicitly. Expect result equals 0. These two tests are completely identical. Equals is probably the most commonly used matcher, explicitly or implicitly. Let's now check the simple result class. It has a single value field which can be initialized through constructor. And here is the test. We compare two instances of result class, both with value 0. Why does this test fail? As you see, the test output is not very informative. We expected an instance of result and receive an instance of result. It's a good idea to override the toString method to make the output more meaningful. Here I ask Android Studio to help me with it. Now the test output changes to expected a result with value 0, but actual was a result with value 0. The test should pass if you ask me. So what's the deal? The equals matcher uses the equality operator to perform that comparison. And by default, classes in Dart are compared by reference and not by value, which means by default two different instances are never equal. To make our test pass, we have to override the equals operator. Let me ask Android Studio again. This default implementation is good enough. Whenever you override the equals operator, you also have to override the hashcode getter. Now our test passes. Now let's see what other equality operators are available. This test is pretty similar to the previous one, but now it uses the matcher called same. And again, it doesn't pass. The output says expected the same instance as the result. Okay, let's pass the exactly same instance. This test completes successfully. As you can guess, this matcher ensures that references point to the same object in memory. An interesting related observation. This test also passes. An integer with the value 1 is the same as other integer with the value 1. The reason is, it's actually indeed the same value in memory because it is constant. Whenever you create a constant instance of any class, a single instance is reused across the application. So if I now mark the result constructor as const, this test here also passes. You see, I declared two different const result instances here, but because they are const and the parameter value is the same single instance is shared and thus the test passes. That's why you should prefer creating const objects in your application when possible. It will consume less memory. The next pair of matchers is quite simple. Is null and is not null. Is null checks if the result is null and thus this test fails. Is not null checks if the result is not null and thus this test succeeds. The next pair of equality matchers is also self-explanatory. Is true and is false. Here we assert that 0 is less than 1, and here we check that the opposite statement is false. Moving on to type matchers. The isA matcher helps verify a variable type. Here I try to ensure that integer 0 is of type result, which obviously is not true, and thus this test fails with the following output. Expected an instance of result, while actual is not an instance of result. Can't agree more. In the next test, I check if the result is of type int, and this time test passes. There are a couple of more narrow type matchers. IsList checks if the result is of type list, and IsMap checks if the result is a map. These two tests pass. Now remember our result class. What if it is a pretty common task in our project to check that the result is of a particular custom but popular type? It is very easy to create own narrow type matchers using type matcher class. Here I declare an isResult matcher, and here I use it in a test that successfully passes. Next we have an error matcher. Let's start with error type matchers first. Is argument error, is no such method error, is an implemented error, is exception. There is plenty, and they are all based on the type matcher class from the previous example. Next is a throw a matcher that ensures that method call resulted into an error. If the method call is supposed to throw, it's unsafe to call it in the test body. Instead, it should be called inside the expect call. That's why here I declare a function that throws an exception, and here I call it inside expect. The throws a matcher accepts another matcher that validates the error, for example, the isException matcher from above. Here is another interesting example. I declare a function that accepts an integer, treats it as a dynamic, and attempts to call lengthGetter. Obviously, integer type doesn't have the lengthGetter, and thus the function fails with no such method error. And that's exactly what this test expects, and thus passes successfully. Next, to collection matchers, and by collection I mean string, iterable, and map. The first pair of matchers are isEmpty and isNotEmpty. Here I have an empty array, and thus this isEmpty matcher is satisfied. Here I have a non-empty string, and thus isEmpty matcher fails the test. And here I have a non-empty map, and this isNotEmpty matcher is satisfied as well. An interesting thing happens when I try to apply isNotEmpty matcher on an int. The test fails with the following output. Class int has no instance getter isNotEmpty. The thing is, isNotEmpty matcher literally calls isNotEmpty getter on any value it was given by casting it to dynamic first. That's why it works for strings, iterables, and maps, but not for integers. Next matcher has length, checks the exact collection length. Here I apply it to a single character string and test passes. Now again I attempt to call it on an integer and receive an error that actual has no length property. The hasLength matcher follows the same principle as isEmpty and isNotEmpty matchers and calls .lengthGetter on the passed value. Let's now look at the contains matcher. It has different logic depending on the value it's applied to. For a string, it means substring matchers. For a map, it means that the map has the passed key. And for an iterable, it means that it contains an element that satisfies the matcher that is passed inside the contains matcher. In this test, first I use a predicate matcher and then an implicit equals matcher. And finally, the isIn matcher is the opposite of the contains matcher. Here it's called for a string and here for a collection. In addition to the collection matchers we just talked about that work for strings, here is a couple of matchers more. The pair of matchers starts with, ends with, check string content in the beginning and in the end. And the matches matcher can either accept another string as here or a regex as here. In addition to those collection matchers that work for list and set, there are a few more matchers specific to iterables. The everyElement matcher verifies that all elements match the matcher that it accepted as a parameter. It is another example of how matchers can accept other matchers, which makes this mechanism so powerful. Matcher anyElement verifies that at least some elements satisfy a matcher or equal to a value it accepted as a parameter. Matchers contains all and contains all in order verifies that iterable passed as a parameter is a subset of the actual iterable. Contains all in order also cares about items order. The actual iterable can have additional elements. Matchers ordered equals and unordered equals check that the actual iterable is of the same length and contains the same elements as the passed iterable, optionally verifying items order. And wrapping up on the collections topic, just a couple of matchers for maps. The contains value matcher checks if the contains value method of an actual value returns true. And the contains pair matcher checks both pairs key and value, where value can be another matcher or the exact value. Next up are numeric matchers. The first group is zero-oriented matchers. Is zero, is non-zero, is positive, is non-positive, is negative, is non-negative matchers all check how the actual value is related to zero. In inclusive range, in exclusive range matchers check if the actual num value is in the range inclusive or exclusive. So here 1 is at the edge of the range, but because it's exclusive, the test failed. Next group is of comparable matchers. Matchers greater than or equals to, less than or equals to, use operator equals, operator less than, and operator greater than to compare expected and actual values. It's pretty simple for built-in types like integer here. They can be applied not only to numeric values but also to custom types, like a greater than matcher here. To use them with our result class, it has to be improved with operator less than and operator greater than implementations like this. Here I compare the value fields of this and other. Because we also have equals operator override, this less than or equal to matcher also works. You can even go further and compare custom types to built-in types, like I attempt to do here. I compare a result of 1 with integer 0. For that I had to enhance operators implementation to work with integer. Now these two tests also pass. Now let's talk about a universal matcher predicate. Generally speaking, most types of checks a developer might ever need to perform in expect function can be expressed with this single matcher. It accepts a predicate, a function with one parameter that returns bool, where you can decide if the parameter matches your expectations. It's that simple. I guess now you might be a bit confused as to why I was telling you about all those matchers if there is a universal predicate matcher. Well, depending on the type of required check, predicate might be exactly a matcher you need. But let's see this failing test here. All it says about the expected value is that it should satisfy a function. Not very informative. The output can be improved with the description parameter, like here. The output of this test is better, but let's compare it to the plain equals matcher we discussed in the beginning. Expected 0, but actual was 1. Same level of details with less code compared to the predicate matcher. So I suggest to always prefer using focused matchers when available. Now to a bit of an advanced stuff. If among all this variety of matchers you didn't find a matcher that satisfies your requirements, or if you anticipate performing a completely custom check quite often, you can create your own matcher. Remember our result class here. I don't let you forget about it, right? Here it has a value field. Let's say I want to create a custom matcher that would validate a value of a value field. For that we need a child of custom matcher class. In its constructor it accepts a matcher to validate the field value. The parent constructor accepts 3 parameters: feature description, feature name, and the matcher. So here I pass these values. They are going to be used in the failed test output. And finally, I have to override the feature value of method that gets the value property. We are basically using the same approach as some of matchers we saw before, like isEmpty or hasLength, calling value on a dynamic type. So our matcher is supposed to work with any type that declares the value property, like the result class. In case actual does not declare such a property, our feature value of implementation will throw, but the base custom matcher class calls it inside try-catch block and will fail the test gracefully. Now I'm creating an instance of this matcher with 0 parameter, and it successfully verifies that the result object has value field with value 0. To be consistent with common practices of declaring a matcher, let's also declare a factory method to create our matcher like this. And here I use it in another green test. And finally, let's see how the matcher behaves when the test fails. The responsibility of a matcher is not only to verify some condition, but also to create a meaningful output. We see that it expected an object with value property of 0, but actually was result object which has a value property with value 1. Strings that I passed in the parent constructor were used to form this informative output. Nice! It's also cool that hasValue matcher can accept other matchers that characterize the expected result. For example, equals, is 0, less than 1. Next in our topics list is matcher operators. The all-of matcher allows combining multiple matchers and ensures all of them are satisfied. It can be used with up to 7 individual matchers or with an array of matchers, which can be seen in its signature. In case of failure, the output prints error from the first failed matcher. Obviously, the result class doesn't have the length property. The any-of matcher also accepts an array of matchers or up to 7 individual matchers and ensures at least one of them is satisfied. And finally, the is-not matcher calls the inner matcher and inverts its matching result. How are you doing? We're about halfway through and there is some more exciting stuff ahead. We are moving on to some asynchronous stuff. Here is the test with an asynchronous expectLater function. Let's check its signature. It looks pretty familiar, doesn't it? The expectLater function is just like expect, but returns a future that completes when the matcher has finished matching. And it has all the same parameters as a regular expect. While expectLater can accept any matcher, it makes sense to pass children of async matcher class, which does asynchronous computation. To future matchers. The completion matcher accepts the matcher to verify the future result. It is basically equivalent to awaiting a future and asserting its result with a regular expect. I can only see it being used in a combination with other asynchronous matchers like this throw-a matcher, which should be already familiar. It checks the future error. Let's check stream matchers next. Here I create a stream with a single value that can be listened to multiple times. The emits matcher checks that the stream has emitted a value that satisfies a matcher that emits has accepted as a parameter. It may accept the expected value, another matcher that characterizes the expected value, or a predicate function. All of these are valid. The never emits matcher performs the opposite check. And these are all valid again, because I changed the stream emitted value. Emits in order ensures a stream has emitted multiple events in a particular order. It accepts an array containing expected values or matchers. Emits in any order is just like emits in order, but it doesn't care about events order. And finally, the emits done matcher helps ensure a stream doesn't emit any more unexpected values. And the emits error matcher helps ensure a stream has emitted an error and accepts another matcher to verify the exact error. So far we tested streams that contain hard-coded values, which were emitted immediately. But imagine we have to test a stream that was already closed, or a stream that has already emitted values we are interested in. Let's take a look at this class. It has a broadcast stream controller, exposes its stream, and has a doWork method which causes the stream to emit two values, 0 and 1. Let me try to test this class. Here I create an instance of a stream example, call the doWork method, and expect stream to emit two values. Unfortunately, the expect function here is called too late. Emitted values are already gone, and this test never completes. Instead, expect or expectLater should be used before the work call. First, we set up the expectations and then perform an action that would lead to events we expected. Here I'm using expectLater without await, otherwise the test will hang on it again. Now we're entering the area of widget tests. Just a reminder, I'm not going into details of how to write widget tests in general, how to search for widgets in widgets tree, but I only focus on the assertions and matchers that can be used here. I will be declaring very simple widget trees to demonstrate how widget matchers work. Once again, imagine your more complex widgets being instantiated here instead. Flutter widget tests use the same expect function to verify that the actual widget tree content matches expectations. However, the list of matchers is unique to this task. Let's start with finds nothing. Here I declare a text widget with text1, place it in the widgets tree, and try to look for widgets with the text 0. As expected, there are no such widgets, and this finds nothing matcher, which ensures no such widget is in the widget tree, is satisfied. The finds widgets matcher ensures that at least one such widget is in the tree. So here I have a column with two text widgets with the same text, place it in the widgets tree, and use finds widgets to look for the same text. This test passes. However, an identical widget tree doesn't pass the next test, where I used finds one widget matcher, because its task is to ensure there is exactly one widget in the tree. And we see in the output it complains that there were two widgets with text1, which is too many. The same is with the next pair of matchers. Finds at least n widgets, can tolerate more widgets in the tree that it was asked to find, and finds n widgets, expects exactly n widgets in the widgets tree. It's not the rare case when we need to test the colors of the screen. Most often it happens when we reflect some operation success or failure with green or red colors. There is a matcher for this task as well. Here I declare a green container, look for it in the widget tree, and use isSameColorAs with colors green parameter. And here is another example for the text widget color. Next pair is in card, is not in card, helps to verify that widget has at least one card widget ancestor or no card. A few words about testing errors in the widgets tree. We all know how container widget cannot have both color and decoration due to this assert in the source code. So here I have a function that would attempt to build a container with both color and decoration, and of course it would fail. If I was a developer implementing container, this test and throws assertion error matcher would help me verify my widget throws the correct error when used improperly. Another interesting matcher is throws Flutter error, and here is a scenario where it can be used. Here I declare a key, which I don't append to the material app but simply provide to a sized box, and then I attempt to reach the navigator using its context, which leads to the Flutter error. Actually, this example comes from the Flutter framework source code itself. If I had to pick one of the most exciting finds from this cheat sheet, it will be this: accessibility testing. In accessibility tests, the first thing we have to do is to enable semantics by creating such a handle, and we have to remember to dispose it in the end of the test. Next, in this test, I declare a widget we are going to test, a square-sized box of size 46 with enabled gesture detector as a child. Next, I place it in the widgets tree, and we are ready to test. Here I'm using the meets guidelines matcher. It is asynchronous, so I'm using it inside expectLater assertion function. Let's check the matcher documentation. It says, asserts that the currently rendered widget meets the provided accessibility guideline. And here is an example usage, pretty similar to what we have in our test. So this matcher ensures that our widget meets some accessibility requirements, which it accepts as a parameter. Back to our example, here I use iOS Tap Target Guideline. Let's check. A guideline which requires tappable semantics nodes a minimum size of 44 by 44. In our test, we have a gesture detector inside a 46 by 46 sized box, so this test passes. Let's check a similar test. The widget tree is completely the same, a 46 by 46 gesture detector, but this time I use Android Tap Target Guideline, and the documentation says it requires tappable semantic nodes a minimum size of 48 by 48. Our tap area is smaller and thus this test fails. And the output explains the reason. Expected tap target size of at least size of 48 by 48, but found size of 46 by 46. Isn't it cool? With just a few lines of code, we are capable to test widget trees to detect small tap areas without running the app and manually clicking through it, and without any special knowledge on the accessibility topic. Let's see how can we detect another common issue, which is text contrast. For this test, I create a white container with a black text inside. And then I test for the text contrast guideline, which according to the documentation requires text contrast to meet minimum values. So black text on a white background has a perfect contrast, and this test passes. Now I'm going to test the same white container with orange text in it. This test fails with the expected contrast ratio of at least 4.5, but found 3.03 for a font size of 14. As you see, the output mentions that the expected contrast ratio depends on the font size. In these two tests, when no style was provided in text widget nor in material app, the default text size of 14 was applied. Now in my next test, I keep the same white background, same orange text, but I increase the font size to 20. And this test passes because larger texts are easier to read even when the contrast ratio is not perfect. This wraps up the accessibility topic. I hope you are as excited as I am about this new find and will care more about accessibility of your apps, given how easy it is to do with Flutter. The last topic for widget tests is testing against golden images. A snapshot of your widget tree can be tested with an in-memory image or an image file. Here I create a container with some padding and a green color inside, place it in the widget tree, and use a matches reference image matcher with an image object, which I created manually by using Paint and Canvas. This technique is suitable for testing low-level widgets that involves custom paints. For the next test, we have a blue rectangle surrounded by a white border. Here I use Matches Golden File Matcher that allows validating that a finder, a feature of UI image or a UI image matches the referenced golden image file. Here is the golden image I prepared, and this test passes. And finally, the last topic for today is testing mock invocations and parameters. So far, we have used expect or expect later functions to compare the results of some operations with the expected values. There is another category of checks developers constantly perform, ensuring that some side effect was triggered. For that, I am using the mocktail package. Here is the service class we are going to mock today. It has a single side effect method with two parameters, and here is the mock object that implements service. Typically, you would pass such a mock to a software under test and then would verify that your software performed the required calls. Here I'm going to manipulate this mock directly. To ensure that a method of a mock object was called, there is a verify function. Here I create an instance of a mock service class and immediately verify that its side effect method was called. Obviously, such a test fails. In addition, you can specify how many times the mock method should have been called. And in case you want to ensure a method was not called, here is the verify never function. This test passes because we actually never called the side effect method. Now to the interesting part, which is testing the function invocation parameters. In case their values do not matter, just use this any object that can represent literally any value. Here I manually call the side effect function with some values and this test passes. In case you know the exact values of expected parameters, just pass real values instead of any. It gets more interesting in case you only need to check those parameters meet some condition. For that, use that parameter of any function, which can accept one of the matchers we looked so closely at before. Here I apply is0 matcher to the first argument and a combination of isResult and hasValue matchers for the second parameter. So that parameter of any function can accept any of all the matchers we talked about today. This wraps up test assertions topic for today. We covered a lot of interesting and useful stuff today. All the details can be found in these two posts in the Invertase blog. There you can also find an interactive Zap project with all the code I shared, or go to my GitHub to download the project locally. Happy testing!
All right. It was hi Anna, how are you?
Hey, great. How are you doing?
Fine. It's nice to have you here. It was a really interesting video, right? That we saw about all of the matchers. So yeah, let me see if we have like any questions. I invite the audience to ask anything related to Anna's presentation. And yeah, in the meantime, okay, there is one question right now. Maybe we can start with that. So let me show it first. Okay, so the first question will be, can you share some of the most challenging problems you faced while developing with Flutter and how did you overcome them?
That's a great question. Well, Flutter is still a young framework, right? And this has consequences in many areas. My biggest challenge 3 years ago was to find my first Flutter job. It wasn't that popular back then. Nowadays, because Flutter community is still young, there aren't many mature approaches to Flutter app architecture, and they only start to being established and gain popularity in the community. So it seems like every team has unique approaches to common development problems. And that's why I talk about topics like app architecture, building network layer, using code generation, writing tests to help us all being consistent and effective.
Of course, yeah. Flutter isn't so opinionated, so yeah, when you start with Flutter, it's like really difficult to know like what are the best practices that we have to use, right? But yeah, we have another question here. Let me show it. So the question is, how does Flutter handle performance optimization, and what are some of the performance optimization techniques you've used in your Flutter projects? This is not necessarily something like so related to the presentation, right? But it's a
yeah, of course, no worries. So first of all, let's give Flutter some credits. It is already quite performant, right? And most of the time, it's the way the layout is implemented causes some performance issue, not the framework, most of the times, right? So the technique number one I suggest to follow is to keep your widgets small and cut your widget tree in layers pretty often. This way you're creating repaint boundaries, and Flutter will know when to stop repainting if it needs to repaint just a small part of the screen. And another thing to keep in mind is that even if your application performs some operations slowly, but remains responsive and intact while performing this operation, it's better than if it performs the operation quicker but has some chunks. And One thing that might cause such junks is performing long synchronous operations in the main thread, like, for example, deserializing a JSON. So to overcome this situation, I suggest spawning an isolate and perform your calculations there. It will take a bit longer, but overall, the application will only win from this.
Perfect. Okay, we have another question that is related to tests, so I'm going to show that first. So the question is, what's the main objective of the golden test for you?
So as I showed today, there are different approaches to testing widgets. We can replicate the widget tree and make sure certain widgets are there. We can, or we can compare the widgets tree we built with an image and a snapshot of how the ideal widget should look like. It's called golden. So today I showed two matchers to which we can give either an image file or to create an image with Canvas and Paint and compare our real widget tree with this golden standard to detect if we have mismatch. Because with simple widget tests, it might not be very handy to test some shadows or some colors, maybe. Yeah.
Great. Okay. So yeah, my last question, like that I was thinking in all of this cheat sheet was if there is anything more to add, like what is the roadmap for the cheat sheet? It's like you did cover everything, or you are thinking of expanding that in the future?
So at least at this point in time, I would say it is done. But here my goal was only to touch about the assertion part of the entire testing. As we know, there is a testing pattern, arrange, act, assert, where you prepare your mocks or your test data, maybe you call some operations, and then only an assert. So I covered this last part of the test. I didn't cover how to structure tests, what is the best approaches there. But I believe there is already quite a number of resources about testing in Flutter.
Perfect. Okay, awesome. Okay, so yeah, that was the last question, and yeah, it was nice to having you here, Anna. I don't know if you want to say anything more or.
Thanks for the invitation. Thanks for this chance to present this resource. I hope it was helpful, and as I said, happy testing.
Awesome.